All right, guys, Mr. Antonucci here, and in this video, I'm going to show you how to integrate an improper rational function in a case where you have to use long division. But before we get into that, I want to talk to you about proper and improper rational functions. So if we let r of x be a rational function, it would be a polynomial function of a p of x over q of x. In other words, it's a rational function by definition is a ratio of two polynomials together where p and q have no common factors. So the domain is going to be all numbers for which the denominator is not equal to zero. We'll be okay there. It's called proper when the degree of polynomial p is less than the degree of q. So degree of p is less than the degree of q. It's called improper if the degree of p is greater than or equal to the degree of q. This is very similar to just rational numbers. So for example, if you had 3/4, that's a proper fraction. If you had 4/4, that could be reduced to 1. And if you had 5/4, it's called an improper fraction, and you could rewrite it as a mixed number 1 and 1/4. Same kind of thing with rational functions, except you're dealing with the highest exponent being the degree. So if you have an improper rational function, then you can use long division to simplify it. So let's look at an example to get the ball rolling on this. If I want to integrate x squared over x minus 1, I would use long division here. So you set up x squared here, and you always want to have the terms accounted for all the degrees below whatever the highest exponent is. So x squared, there's no x term and no constant term, so I put 0x plus 0, and I'm dividing by x minus 1. Okay, so I think, what times x will give me x squared? Well, I'd have to multiply by x. So x times x minus 1 is going to give you x squared minus x, and then you subtract those. These cancel, and you have 0 minus negative x, which would be x. And then you would bring this number down, but it's just 0. I'm just going to do it for consistency's sake. And then again, x times what number or what is going to give me x? Well, you'd have to have a 1 there. So 1 times x minus 1 is x minus 1. If you subtract those cancel, and then you have 0 minus negative 1, which will give you 1. Now, this is the remainder because the degree of 1 is less than the degree of what I'm trying to divide by, which is x minus 1. So since the 1 is positive, I would write it as plus 1 over x minus 1. Now, this integral becomes x plus 1 over x minus 1 dx. And now I can actually integrate this because I can think of it as the integral of x dx plus the integral of 1 dx plus the integral of 1 over x minus 1 dx. The integral of x is x squared over 2. The integral of 1 is 1, and the antiderivative of 1 over x minus 1, well, that's u prime over u. It lines up perfectly, so this is natural log absolute value of x minus 1 plus c. Don't forget your plus c on there. Okay, so that's how you do it for that one. The next one we're going to look at here is another example. Do this one here. You have x cubed plus 5x plus 10 all over x squared plus 1. So what we're going to do is use long division again to rewrite the function in proper terms. So you'd have x cubed plus 0x squared plus 5x plus 10, and divide that by x squared plus 1. And then I'm going to actually pause the recording and go through the long division just because it takes a lot of steps and it's going to take some time. But then I'll leave the work up there and you can pause the video if you want to check out all the steps there. Just kidding. It actually doesn't take too many steps because you have to think x squared times what gives you x cubed. That already gives us an x here. So x times x squared plus 1 is going to give you x cubed plus x. Now, notice how I'm lining up my columns with my terms. You subtract the x cubes, cancel, and then you have 5x minus x, which gives you 4x plus 10, bring the 10 down. And now the degree of what's left is less than the degree of what I'm trying to divide by. So I would just write 4x plus 10 over x squared plus 1. Okay? And since the 4x plus 10 is positive, it's going to be plus. So this integral becomes x plus 4x plus 10 over x squared plus 1. Now, I see a couple things here. The 4x plus 10 is not the derivative of x squared plus 1, and I can't, manipulate it by multiplying or dividing by a constant, because all the derivative of x squared plus 1 is 2x. I wouldn't have anything for the plus 10 in there. But what I can do is separate it like this. Where I break apart the numerator into two separate fractions. But remember, when you break apart a numerator into separate fractions, you have to put it over the same denominator. So they both have to be over x squared plus 1. The antiderivative of x dx is x squared over 2. The 4x over x squared plus 1 is almost u prime over 2. Like if I let u equal x squared plus 1, then du is 2x dx, and I'd multiply both by 2, and you'd get 4x dx. So what ends up happening in that case is you would have 2 natural log absolute value of u, which was x squared plus 1, plus, now for this last one, you can think of that as inverse tangent, because I can factor the 10 out like this. And then this is just going to be 10 tangent inverse of x plus c. Okay, so let me neatly write our answer out here. So we would have x squared plus 2, x squared over 2 plus 2 natural log of x squared plus 1. Now you don't need the absolute values here because x squared plus 1 is always greater than 0. So the absolute values only account for if the argument in there it could be negative, which it can't. So plus 10 tangent inverse of x plus c. Okay. All right. So good stuff on that one. All right, our sixth and final example here is we're going to use long division again. Notice we have an improper integral because the numerator's exponent is greater than the denominator's exponent. So we would use long division. I'm just going to kind of wave my hands over it and say, boom, we did the long division. So this is going to become integral of x plus 2 plus 5 over x squared minus 6x plus 10 dx. Okay, now that first part, the x plus 2, we can easily integrate that. So I'm going to pull that off to the side as x plus 2 dx plus the integral of 5 over x squared minus 6x plus 10. Now, x squared minus 6x plus 10, we would need to complete the square on that. Now, I know that x squared minus 6x, oh, I forgot the 0 there, plus 9 is a perfect square of x minus 3 quantity squared. So all I have to do is rewrite the 10 as 9 plus 1, and then group the first 3 terms together and be x minus 3 squared plus 1. So I'm going to integrate the x squared, or the x plus 2, so x squared over 2 plus 2x plus, now I didn't integrate this, I'm just going to rewrite it as 5 over x minus 3 squared plus 1 dx. Now here, we can let u equal the x minus 3 and use the tangent inverse. So u equals x minus 3, du equals dx. So we would have x squared over 2 plus 2x plus 5. I'm going to factor that out over 5 times du over u squared plus 1. And then we can anti-differentiate now. So x squared over 2 plus 2x plus 5 tangent inverse of u plus c. And then again, we can back substitute what the u is here and get x squared over 2 plus 2x plus 5 tangent inverse of x minus 3 plus c. Okay, so that ends up being our final answer for that one. All right, guys, hope that was helpful to you. Make sure you reach out if you have any questions. Take care.